Okay, let's dive right in. We are at this incredible moment in medicine, where AI is promising to completely change how we diagnose diseases. But here's the thing, to make these AIs super smart, they need a ton of our data. And that, right there, creates this huge dilemma. How do we get these life-saving, accurate diagnoses without giving up our privacy?
To really get what's at stake here, let's just start with a really direct question. We trust our doctors, right? Especially the specialists who read our x-rays. But is it possible that a machine, just a piece of code, could actually do a better job?
Well, the answer might actually surprise you. In many cases, yeah, it can. This chart shows what's called an F1 score. Think of it as a grade for accuracy, where 1.0 is a perfect score. In a major study on hip fractures, the AI model hit 0.94. Now that's not just good, that's a little bit better than experienced orthopedic surgeons and a lot better than general radiologists.
And this isn't just a one-off. Using AI like this could slash the number of missed fractures by almost a third. I mean, the potential to improve patient outcomes is just massive. But, and this is really the whole point of our explainer today, there is a huge catch. See, to get that good, an AI has to learn from millions and millions of examples. That means taking all our sensitive X-rays, our MRIs, our private patient files from hospitals all across the globe and dumping them into one giant centralized database. You can probably see the problem here, right? It's an ethical, legal, and security nightmare just waiting to happen. So, how on earth do you solve that?
Well, the solution is this incredibly clever idea called federated learning. The core concept is simple but brilliant. Instead of bringing the data to the AI model, you bring the AI model to the data. It lets all these different hospitals work together to train one super powerful AI, but without ever having to share a single piece of private patient data.
Here's a really easy way to picture it. Imagine every hospital is a private library, and the patient records are these super sensitive, unique books. Now, instead of making copies of all those books and shipping them to one central library, which would be a huge risk, we send a very smart librarian, that's our AI model, on a tour. The librarian goes into each hospital's private library, learns from the books right there on site, and only takes away general notes about the patterns it sees. It never actually copies or removes the books themselves.
So how does this whole librarian tour actually work in practice? Well, it's this really elegant cycle. First, each hospital gets its own data ready. Then, the main AI model is sent out to each one, and it trains inside each hospital's secure walls. Now, here's the magic part. The only thing that gets sent back to the central server are the learning updates, those general notes the librarian made. The actual patient data never ever leaves the hospital. The central server then averages all those notes together to create a new, smarter AI model, and then sends that back out to the hospitals to start the whole cycle over again.
And we're not talking about some simple little program here. These are incredibly complex models, like the one you're looking at, which is used for classifying skin cancer. This entire sophisticated thing gets trained locally at each hospital, all while the patient images it's learning from stay completely private. It's an amazing solution, but it's not quite perfect.
Which brings us to a really critical question. Okay, we know the raw data is safe inside the hospital. But what about those learning updates? Are the librarian's notes really, truly anonymous? Or could a clever hacker maybe piece them together and figure out what was in the original books?
And the tricky answer is, not always. Researchers have figured out that, in theory, it might be possible to reverse engineer those updates. There's this thing called a model inversion attack that could potentially reconstruct sensitive details about the very patients the system was built to protect. So, we're going to need another layer of security.
And that extra layer is called differential privacy. It's basically a mathematical guarantee. It's a way of sharing insights about a group while making it impossible to learn anything about any single individual within that group. You get to see the forest, but the individual trees are completely hidden. Let's go back to our librarian analogy. With differential privacy, before our librarian sends those learning notes back to the main office, it intentionally adds a little bit of carefully calculated fuzziness or noise to them. This statistical noise makes it mathematically impossible for anyone to link any piece of information back to a specific patient. It's pretty much the ultimate privacy shield.
But, and you knew there was going to be a but, right? This incredible ironclad layer of privacy isn't free. Adding noise, even when it's done very carefully, has a direct consequence. It creates a fundamental trade-off.
And this chart lays that trade-off bare. Look at the baseline model. That's if we just threw all the data in one place. It scores around a 0.91.
Okay, pretty good. Now, using federated learning to protect the data brings it down just a tiny bit to 0.88. Still great. But then, when you add that ultimate guarantee of differential privacy, the score takes a more noticeable hit, dropping down to about 0.81. And this is the core dilemma. Historically, more privacy has meant less accuracy.
So does that mean we just have to choose? Do we want a more accurate AI or a more private one? Well, not necessarily. Researchers have found a way to get the best of both worlds by being really strategic about how and, more importantly, when they add that privacy noise.
They do it using this clever trick called an adaptive privacy budget. The basic idea is that the AI model learns the most important stuff at the very beginning of its training. So you let it learn more freely in those early stages with less noise. Then, as the training goes on and the lessons learned get smaller and smaller, you start cranking up the privacy protection. You spend your privacy budget when it will have the least impact on the final accuracy. It's a really smart way to balance things out.
And this isn't just some theory cooked up in a university lab. This combination of federated learning and differential privacy is actively being built and tested for some of the most complex, high-stakes fields in all of medicine.
I mean, just take spine surgery. This tech is being looked at for everything from predicting how well a surgery will turn out to helping surgeons map out their plan on an MRI. It's enabling research across dozens of hospitals that could never happen before, and it could even be the foundation for things like robotic telesurgery, all while keeping patient data completely locked down.
So here's the real takeaway. The future of medical AI isn't some black and white choice between getting the best diagnosis or protecting your privacy. It's about smart engineering. It's about finding that perfect balance point between the two so we can have these incredibly powerful tools that we also trust with our most sensitive information.
And that leaves us with one final question. And this one isn't for the engineers or the researchers, it's for all of us. When it's your health or your family's health on the line, what's the right balance for you? How much potential accuracy are you willing to trade for an absolute guarantee of privacy? It's a tough question, and it's one we're all going to have to think about as this technology becomes a bigger and bigger part of our lives.